Hello and welcome. This is second video on second lecture on the lecture series called Classical Electrodynamics 1. In the last lecture, I gave the brief explanation of Maxwell electromagnetic equation or Maxwell equation of electrodynamics. And in this video, before exploring those mathematical equations, we have to familiarize ourselves with some basic mathematical tools, and one of the mathematical tools is vector analysis. Basically it is the differential calculus of vector. We know that electricity and magnetism in mathematics represented by the field, uh, vector field as well as scalar field. So in electrodynamics basically we study two kind of field, vector field and scalar field. So this is some review of the concept from the vector analysis. Here is the vector A and vector B, and dot product of any two vectors always give scalar as output. It means A and B are two vectors, and if there is a dot product between these two vectors, then there is a scalar output. It will give scalar as output. So A dot B is equal to AX, BX, AY, BY, AZ, BZ. It means simply the dot product of components of A and B. Now there is also a cross product between two vectors, and cross product of two vectors gives vector as output. And here, because cross product gives vector as output, it means it has three components. So A cross B component, A cross product of A cross B, Z component, Y component and X component. So Z component is AX BY minus BY AX, AZ BX minus AX BZ, AY BZ minus AZ BY. So in the metric form we can write what we call AX, AY, AZ, B, BX, BY, BZ, I, J and K. This is the cross product. So this can be represented by this one. Again, there is another concept. If cross product with itself, if there is a vector A and if there is vector A and cross product of vector A with itself always give 0, and this one cross product of A, dot product of A, dot product of A with cross product of A cross B gives 0. A and B are two vectors, and if we multiply this A cross B with A, it means dot product, it means gives 0. Again, A dot B cross C equal to A cross B dot C, and A cross B cross C equal to B A dot C minus C A dot B. These are some important concept in vector analysis. Now, the simplest field we can imagine is the scalar field, which is only represented by a number, a scalar, and this number only depends on the position in the space. Example of the scalar field, one of the example of scalar field is a metal which heated at one place and at on another place it has been cooled down. It means it has uneven temperature. It means the temperature is a scalar field. Only we have to know about the value of temperature, which is the function in this case, which will be the function of position in the space. Now we represent scalar field by contours or continuous line, and in case of that metal body, which in case of the temperature we draw called isotherm, and this is the isotherm. Each line represent a different temperature, and this arrow is called heat flow. It is heat flowing from hot to cold, and heat flow is the directional quantity, and this temperature is a scalar field, and this but heat flow, which is flowing from hot to cold, is the vector quantity. It means scalar field is only a number, but vector field number plus direction. So in case of the heat flow, we have what we call vector field, and this is the heat flow. These lines are the heat flow. It has specific direction, and heat flow is the vector field. And if H is the heat flow, N is the what we call normal along the surface A, then H dot N is the heat flow normal to the area. So these are the some example of scalar field as well as vector field, and how we differentiate between scalar field and vector field. Vector scalar field are only numbers, depends on the position. Vector fields are the what we call numbers, magnitude plus direction, in which direction vector is indicated. Now we know that field varies place to place, also in time. It means we have to somehow find the variation of field from point to point or in time. It means we have to know their derivative with respect to time as well as derivative with respect to position. And derivative, DERI, derivative del by del x or del by del t is nothing but a variation with respect to x and with respect to time. So variation in position x and variation in time with del by del t. This tells about the specific value of the field at a specific point and a specific time. Suppose x, y, z are three coordinates, component of the coordinates, and suppose t is the scalar field, then del t by del x, del t by del y, del t by del z, these three are the derivatives along the x, y and g. So grade t or gradient t is equal to del t by del x I del t by del y del t by del z, and this gradient t is the vector. So gradient, this is del or grade of something scalar quantity, always give the vector, and this has some very important application in electrodynamics. So we have to remember the variation of field indicated by the gradient, and gradient is nothing but a variation along the x-axis, y-axis and z-axis, and grade is equal to del y del x plus del y del y plus del y. This is nothing but a operator which can operate on any scalar field. So this is called gradient, and this has very important application in electrodynamics.